All right, we'll get started now. So thank you everyone for coming to our presentation. Um, as Kevin said, my name is Julia, and well, my teammates are Roger, Sherry, and Alina. We have our videos on just so that you can see us when we speak. First, I just wanted to give you a quick overview of the presentation today. So I'm going to give a quick introduction to the project and a bit more context on Surrey. Then we're going to talk about two indices that we developed for our project. Third, we're going to talk about the statistical models we built. There are two of them, one for pedestrian AADT and traffic AADT, and we'll get into what that means later into the presentation. And finally, we're going to give you a demo of the Shiny app we built for the people at the City of Surrey, so that you get an example of how our final product looks like. All right, so Surrey, it's the second largest city in Metro Vancouver, and it has seen an increase in the number of commuters who use public transit, so that also means more pedestrians. And it's a city whose population is also increasing in size. Another important fact is that cyclists and pedestrians, they only make up for 5% of commuters, but then they're overrepresented in traffic fatalities as victims of harm. So 50% of traffic accidents involve pedestrians and cyclists. Currently, the way the City of Surrey decides to build a crosswalk, there are the technical criteria in which pedestrian volume and traffic volume are important considerations, but they also rely on residents submitting service requests. So in this way, they can focus on certain areas depending on these requests. The City of Surrey implemented the Vision Zero project recently, and its overall goal is to improve mobility, especially vulnerable road users. And another important factor is to improve equity, because they have identified that communities with a higher percentage of a low-income population, they have higher pedestrian collisions, and at the same time, they have a lower number of crosswalk service requests. So our project goals are to determine the factors that are important in planning a new crosswalk and develop measures that help quantify the need for a crosswalk. Then we wanted to create a model to predict pedestrian and traffic volume for each intersection. And last, we wanted to build a tool, which it's an app to visualize and analyze results. And overall, of course, the overarching goal is to provide a data-driven approach that can inform better policy decisions in terms of implementing crosswalks. And in summary, our approach, well, first we decided to develop a measure, and we did that by gathering information on how different cities plan for pedestrian safety. So we found these two indices that were built by the City of Portland originally for determining sidewalks and where to put them, where to improve them. And we decided to take them and adapt them for this project. So the two indices are the deficiency index and the potential index. Then we decided to build a model that predicts pedestrian and traffic volume, so that we could predict it for every single intersection. And at the same time, we wanted to find the factors or covariates that are important for these two predictions. And lastly, we designed the visualization and the Shiny app for the user to be able to see the results and adjust them, and give them flexibility to use the tool to different goals or for different purposes.
Okay, I'll take over from here. So in this section, I would like to talk about what pedestrian potential and pedestrian deficiency indexes are. And I will begin with like some previous work on this area, and then the way we adapt these two indices to our case here. Okay, so these two indices are actually originally designed to sort of like quantify the aspects for sidewalk instead of crosswalk. But because sidewalk and crosswalk, they are, well, not the same, but relate to each other. So we decided to use these two indices in our case. So what potential indices is about is for a location to generate pedestrian volume or pedestrian demand. And for pedestrian deficiency index is basically measure the level of necessity for pedestrian facility or improvements. So ideally you want to build a crosswalk in a location that has high potential index and also have high deficiency index. And for those locations that has low potential index or low deficiency index, the need for new crosswalk is probably not as high as other places. Okay, this two indices has been used by a number of cities, so it's useful. So like we sort of like want to use these two indices because their usefulness in other cases. And then in the next slide, I'm going to talk about like how we adapt these two indices to our case here. Okay, so for the PPI, in the original proposal for PPI, they take into several considerations. So one of them is like transportation elements, like the distance to the nearest bus stop, and other regional discriminant, like whether an intersection or a location is in like commercial area or residential area or not, and then school proximity and other distance, another destination proximity, like distance to the closest shopping mall, whether an intersection or a location is close to a park or not, and other environmental factors like, for example, the percentage of population that's commutes by walk or taking public transit. So in our case, we try to approximate these original factors as close as possible. For example, we also have like school proximity and also the distance to other places of interest like library, recreational center, or other places. And we also take into account like employment within walking distance. For example, an intersection that has close to an employment location that has like more than 20 employees will be more important than say an intersection that is in the middle of nowhere. Yeah. And then for other things, we also include bus stop usage and also the distance to existing walkway. So bus usage is obviously very important because like you would expect more people showing up in a bus stop that are more that has more buses or that are in the city center. And then existing crosswalk is that we also take into the continuity of crosswalk. So you probably want to build a new crosswalk in a location where there are already a lot of existing crosswalks. So like everything will be more continuous in that aspect. Okay, and then for PDI, the original metrics take into consideration multiple factors, and a lot of them are related to traffic volume, like traffic speed, traffic volume itself, and also like road width, and also crash factors like the frequency of automobile pedestrian crashes. Okay, so in our cases, we also try to approximate these factors as close as possible. So we also have road width, the number of lanes, and then traffic volume and other factors related to crash or speed. And specifically in our case, because we care about crosswalk, and you probably don't need several crosswalk like that is just like one adjacent to another. So that's why we also take into the distance to the closest crosswalk from a particular intersection. And then in the next slide, I'm going to a little bit more detail about like how we adapt these new factors into our indices. So for bus stop usage, we have the data from transits. The data format is in both temporal and then spatial dimensions. So we have like data all the way from 2014 to 2019 about bus stop usage. And naturally, it's a 2D, in one time slice, it's a 2D dimensional data. So what we did is like, we want to keep both the temporal and spatial information. For this one, we choose to do what is called emergent hotspot analysis as implemented in ArcGIS. And the output of this analysis is a bunch of labels that you can see on the left. For example, there are spots that can be called new hotspots or consecutive hotspots. I will not go into the detailed definition of these hotspots here, but then you can understand that on a very high level, there's a binary distinction. So like hotspot will be places where events happen more often, taking into consideration both temporal and spatial dependency. And then cold spot are those locations that's compared with its neighboring value, it's a relatively low value here. So if we look at the results on the right, we will see that for bus stop usage, we don't really have any cold spots. We only have high spots. And then for most bus stop here, so each point here is a bus stop in Surrey. So for most bus stop here, like there's actually no specific pattern. That means like the usage across those spots are probably the same as to the global usage. And then for specific location, you can see some intensifying hotspots or consecutive hotspots. And if you are a little bit familiar with the geography of Surrey, so this is the city center of the Surrey. So like those hotspots tend to be the center of that particular neighborhood. All right, so for the bus usage, we're trying to incorporate the result from emergent hotspot analysis into our factors indices. Okay, and then the next one. So, and then for deficiency index, we focus on, okay, I will focus here on crash score and also the measure related to the distance to the existing crosswalk. So in the original indices, the way they take into consideration a crash score is that for a location, they just draw a buffer zone and then counts how many incidents is happening in that buffer zone. Like here, because we have, again, both temporal and spatial data, we would like to see these two dimensions get taken into account when we are incorporating this factor into our indices. And then for distance to existing crosswalk, we use a relatively straightforward straight line distance to the nearest crosswalk. So I will not go into detail about that, but I will talk more about the crash score. Okay, again, because this data set is inherently both spatial and temporal, so we again use emergent hotspot analysis as implemented in ArcGIS. And in the result you see here, so each dot here represents an intersection in Surrey. So these are basically all the intersections that are in Surrey. And then for each intersection, we can classify them into different categories. So again, in this case, we don't have any cold spots detected by the algorithm, only hotspots. And you will also notice that most collision with intensifying hotspot or persistent hotspot all surrounding, for example, here is the Surrey city center. And then other locations are like sort of like the busiest parts or blocks within the respective neighborhood. Okay, and just to zoom in a little bit on what the more detailed results. So on the left, you can see like a zoom in map, and then each dot here represent an intersection. So because the intersection are like automatically detected using other algorithms, so it's not 100% accurate, but still it's captured the majority of the intersections. So here you can see that intersection here, each intersection will be classified into different categories. And then we assign a score, we assign score for each different categories. I will not go into detail again about like how we assign a score, but we can talk about that if you guys have question in the question period. But here's just show you like the result for each individual intersection. All right, then the next one. Okay, so that's basically about the indices. And in our indices, we actually also take into account like traffic data volume, traffic volume. And then for those traffic volume, because we don't have the data for each intersection, that's why we need to build a model to predict the traffic volume for those intersections that's missing the data. And then Sherry will take over from here and talking about like how we build a model to predict those intersections that's missing traffic volumes.
Yes. In addition to being a factor in our deficiency index, another reason for needing a DT model is that it is the pedestrian volume and traffic volume are two criteria currently used when evaluating a location for crosswalk. So in the end, we want to have pedestrian volume and traffic volume estimates for every intersection. But with the data we have at hand, only 7% of intersections have traffic counts, and some are from as early as 2006, hence could be out of date. Our approach was to first convert the raw traffic count data, typically 7 hours in length, to annual average daily traffic, using the conversion factors provided to us by the City of Surrey. This conversion also gives us a lower and upper bound of AADT. Then we find covariates that we think are related to traffic volume from the data we have. Once that's ready, and once a few spatial and temporal outliers are removed, we can fit generalized additive models, or GAM for short, which allows us to capture spatial correlation as well as spatial temporal correlation if there's any. We will do this for crosswalk users and vehicles separately. Crosswalk users include pedestrian and cyclists. We will refer to the corresponding model as pedestrian AADT model. Vehicles include cars, buses, and trucks, and it will be referred to as traffic AADT model. The next slide lists all covariates that were considered in fitting the models. We used stepwise variable selection by AIC to find the subset of most relevant covariates that minimizes out of sample prediction error. The blue ones are selected by pedestrian AADT model. The orange ones were selected by traffic AADT model. The green ones are selected by both. I won't go into details about the variables as they are mostly the same as our PPI factors, and I believe you will have access to the slides afterwards if you are interested. Here are some model diagnostic for technical minds. Again, I won't go into details, but if you are interested, we can discuss at the end. But just looking at the adjusted R-square and deviance explained, 0.9 and 92.9% are very high, which means that this traffic AADT model fits the data very well. However, our pedestrian AADT model is not as good, with adjusted R-square of 0.38 and 49% deviance explained. If you remember, buses were included in traffic AADT and they have a fixed daily schedule, so this is to some extent expected. We've briefly looked at how well the model fits the existing data, so if you can go to the next slide, please. This slide shows how well the model generalized to unseen data. The prediction performance is estimated by 10-fold cross-validation, assuming the count locations are a representative sample of all intersections. For traffic AADT model, we have 67% of the prediction within the lower and upper AADT bounds, 93.8% of the prediction credible or confidence interval overlaps with AADT bounds, and for those that overlap, 72.2% of the AADT bounds are covered by our confidence interval. Probably more importantly, 88.8% relative border is preserved. Unsurprisingly, the pedestrian AADT model accuracy is not nearly as good. Only 28.1% prediction fall into the AADT bounds, and 63.2 confidence interval overlaps with AADT bounds, and when they overlap, 67.3% of AADT bounds are covered. But fortunately, 75.8% relative border is preserved. So for the purpose of comparing which location is more in need of a new crosswalk, 75.8% relative border preserved can still be of value. After seeing the results, I wanted to talk about the challenges and some sources of error. Firstly, there's error in our response variable. The ADT values were converted from raw 15-minute interval counts, and the adjustment factors were provided for every hour, but we had incomplete hourly counts. So it can go from 8 to 8:15, for example, and then the next entry could be from 8:45 to 9. In these cases, where the first and last interval of the hour exists, we just assume there were 0 counts in between. Otherwise, we discard the hour. Also, the adjustment factors were updated in 2018, but the raw count data that ended up in our training set goes back to 2010. And there were 4 types of adjustment factors considering school and commercial impact, but we only used the typical adjustment factors. This issue is partially addressed by including number of schools and places of interest, which includes shopping centers, as covariates. But the third point is what I think contributing the most to the different performance of the 2 models. The AADT adjustment factors did not differentiate between vehicles and pedestrians. But you can imagine how pedestrian volume is more dependent on the weather, how it has different peak hours than vehicles, and how it will fluctuate more across different hours of the day, different day of the week, and month of the year. In fact, when day of the week was included as a covariate, it was selected by the pedestrian AADT model when it should have been abstracted away by the conversion to an annual average daily volume. We also had some inaccurate covariate values. Income was selected by traffic AADT model, but income information is not available for some dissemination areas. So we took the mean income from its adjacent DAs. Then we had the issue about temporal covariates only available for a limited number of years. For census data, it's only available every 5 years. For bus stop usage, it was selected by variable selection, but we only had data from 2014 onwards. So we couldn't include it as a covariate, as that would cut our training data to less than half. And from our cross-validation results, we decided it's not worth it. We also had issues about spatial covariates not taking into account of the year built. So if pedestrian volume increased because a new bus stop was built this year, the model wouldn't know that. It would get confused and think maybe year is a significant predictor when in fact it's the distance to bus stop. And finally, since training data is only 7% of all intersections, there are categorical variables with values not seen in the training set. For traffic control, since the major types of traffic control were in the training data, we just grouped any special types of traffic control like speed hump and diverters into no traffic control category. And for land use zones, we took an approach similar to KNN, where we make predictions using adjacent zone values seen in the training data and take the mean of the predictions. With that, I'm going to hand over to Alina to show you our visualization app.
Okay, thank you, Sherry. We're just gonna move on to our last part of our talk today. Some features I'd like to introduce to you to our Shiny app before we dive into our demo is 2 things. The first thing is the ability to visualize many places of interest, crashes, schools, onto the layers of the map so that when you do zoom into an intersection, you are able to contextualize it and see what is around that intersection that may have caused a high or a low score in that particular intersection. We also have a pie chart. I'd like to call it a double donut chart. You'll see it later in the demo that shows the breakdown of the PPI and the PDI scores with each of the variables hugging it so that you can see the breakdowns and how the scores makeup of this particular intersection will be. We also have the scores available in the table format as well. The more important part I'd like to say of our Shiny app is the flexibility we offer to the users to customize the parameters for each score so that they can adjust the weighting criteria in a stepwise function. With that, they could use this web app not only for crosswalks, but they could use it for other, the Surrey people can use it for other departments as well if they want to do more sidewalks things, or libraries or school, and etc. Lastly, they will be able to save their new scoring criteria, the results itself, and export the data. So I'm going to reshare my screen to our application demo. All right. So here we see our interface. This is the black lines are the border of Surrey, and each dots you see here are intersections, distinct intersections. And each intersection, you're able to click on them, and there will be a interactive, I guess, pie donut or double donut chart, if you may. And the blue here, you'll see are the PPI, or the potential index scores, and around it are the variables that make up the score. And they are in order, so you can match these together. And the red is the deficiency index. And similarly, we do have the variables there. Depending on which intersection you're clicking at, the variables will change and the legend will change as well, showing only the variables that are present in this double donut chart. Right above it, you can see the pedestrian and the traffic AADT. Sherry just talked a little bit about how we've gotten these values. And I'd like to also introduce you to this part over here where you can choose a certain neighborhood that you're interested in, and the map will show you that neighborhood exactly, and filter out any other intersections that are not in that neighborhood. There are two intersections I'd like to introduce to you here. You can search by intersection. Suppose you want to go to intersection 9. And here you can see that we also have the actual AADT scores for both pedestrian and traffic. And this will be what it looks like. If it's absent, then like you saw, the actual will just be blank. And then this other intersection is a particularly higher scoring intersection. And I just want to walk through of how people in Surrey can use this web app to explore what this intersection is going through, if you may. So the intersection has 47 as their total score, and there are layers you can put in here, such as businesses, community halls, senior facilities, shopping centers, hospitals, parks, transits, which I will not put on because it's just so many of them. You can see any of the requests that the people of Surrey have sent in to build crosswalks. Secondary schools, elementary, and existing crosswalks as well. So here you can see this intersection is relatively close to many shops or many businesses, and two community centers, the Newton Cultural Center, the Newton Community Hall, and a senior center as well. There's a park right here, a water park, and schools right here and here. You can also click on this and see the Euclidean distance between the two. So this would be around 260 meters, or if you're interested, you could do, from this to the school over here and be like, all right, it's under a kilometer. So that gives you a sense of what this intersection looks like. And I actually went ahead and looked at the intersection on Google Maps. This is what it looks like, kind of a busy intersection. You can see a lot of stores over there. And you can see clearly that this one pedestrian has jaywalked to cross the road over here, which can look very, very dangerous. And so as a city planner, maybe they see this and they can look into this intersection a little bit more so that it could maybe build a crosswalk there. So that's it for our mapper. I'm just going to quickly go through the others just in the interest of time. Over here, we have the weighting scheme. So you can see the actual raw data of each variables here. On the y-axis, you'll see the distance in meters to the closest walkway. And then the y-axis, you see the number of intersections within those bins. You can also add these steps if you want to. You can also change the scores over here. You click update and you will see the scoring scheme in red, just overlaying the data itself. You can also delete the steps if you want to. And the existing values we have here are default values in which we have calculated and determined by looking at other cities as an example, and also consulting the people from the City of Surrey to see what kind of numbers make the most sense, but we do want to give the user a little bit more of a flexibility if they choose to change these things. And once they've changed it, once they take it out and stuff like that, or they deem that maybe transit stop is not very important, they can just put this to 0 as well, and that variable will not be included in our map or in a scoring scheme. They could click save, and this does two things. It updates the map and the table of the total scores as well, and you're able to download it so that you have a copy of it for future references too. And the same thing we have for PDI, and the last table here are the specific scores you can see and search for the intersection ID there as well. And lastly, we have the rankings where you can just click here and see the least scoring and the highest scoring intersections here. That concludes the app demo. I'm just going to pass it off to Julia for a very quick conclusion to our project.
Thank you, Alina. So yeah, before we wrapped up, we wanted to also go reflect a little bit on the goals that we were able to achieve, but also talk a little bit about the limitations and the data biases inherent in any project that involves data. So I think we were successful in improving both of the indices because the modeling, especially the AADT model, had a very good deviance explain, and it was reliable. Then we were also able to include the bus usage and pedestrian collision analysis to create a more robust measure and include the time dimension. And at the same time, the collision, the emergent hotspot analyses and the bus usage hotspot analyses are also going to be given to the people at the City of Surrey as independent tools for future use, because they also mentioned that it would be useful for them to have that as a record because it might be important information for other projects. At the same time, well, I think the app, it's going to be very useful to support data-driven policy decisions. And since it gives the user a high degree of flexibility, it enhances the sustainability of the project, because as we mentioned before, it can be used in the future or adapted for other uses. Some of the limitations of our project, of course, are the data that has time associated with it, that it was a little bit difficult to handle. And another part of that, it's, for example, we are not sure of the future interactions of building a crosswalk and how that would impact the PDI and PPI measures. Similarly, we had missing data that of course affects the results. Also for pedestrians, we don't have any disaggregated data for age or any accessibility needs. And of course, we had to adjust the methodology with the data we had. So even though we had methodology from the literature, we had to adjust it for our project needs. And lastly, there are many assumptions that are made of pedestrian behavior that are difficult to address, because they're also based on guidelines like engineering guidelines or provincial and national guidelines. So these are some of the points that that we just wanted to acknowledge. But overall, we are very satisfied with the end product. And can you go to the next slide, Alina, please? We wanted to thank you for coming to our presentation, and also a special thanks to our partners at the City of Surrey, Nathan, Kristen, and Shabnam, for their support throughout the last 4 months, and also at DSSG, Kevin, Raymond, Jean-Francois, Hermine, Joe, and Nick that provided a lot of support. And if you have any comments and questions, we welcome them. So now we're going to open the time for a Q&A. Thank you very much.